Welcome back to Geology for Fun. Today we're going to be talking about the Arctic forests of northern Canada. Yes, I said forests and I said northern Canada. This is very surprising because, well, let me get into where these forests are and then you'll understand how surprising it is. So here we are with United States down here. You got Maine sitting up here, right? Washington State, Puget Sound down here. Seattle's about there. Um, so Alaska's up here. Here's all of Canada. And oh, hey, here is Axel Heidelberg Island. Here's Elsmere Island beside it. Now it appears that Elsmere and Greenland are farther north, but that's actually the latitudes are sliding up in this direction. The Arctic Circle, which north of which during the middle of the winter the sun never rises. It comes up near the horizon, you see a lighting during the horizon, and then it comes back down again without actually the sun peeking across the horizon. That runs from down here somewhere, comes through the north end of this lake, comes through here, comes through the south end of this island, and comes looping up through here somewhere, right? So this is way up there. You've got months of time where the sun never comes up here. This does not have forests growing on it today. In fact, it's largely denuded of any kind of vegetation. It is a very, very rugged, very unpleasant type place to live. People have lived there before, but by the 1900s, when it was being explored, the people had abandoned it because it's not exactly a very hospitable environment. So let's go to the next slide here. But this is what's exciting. You notice this debris here. This is organic material, tree-like stuff, and it's eroding out of the layers. There's some pictures I've seen I didn't have here, but they're showing more sharply defined layering. And some of these are eroding out, and you've got this forest material eroding out of the side of the hill, which is quite unexpected. Here's a tree stump. This area here's eroded down. You got a tree stump sticking out, right? You got this layering here. And I don't want to go into a great deal of detail in this particular video, but whenever you see layers with sharply defined boundaries, it indicates that the sediment was deposited rapidly. There hasn't been an opportunity for plant and animal life to grow in and disturb the boundary and homogenize that kind of material. So this really has kind of a debris flow type environment. And you're like, wait a minute, this is a stump. Why would I say debris flow in a stump? Well, actually, stumps can become part of debris flows. We saw that with Spirit Lake in Washington State when Mount St. Helens went off. It's the trees on the mountainside were ripped off the mountainside and carried down into the lake. And a bunch of the stumps of the trees and trees with stumps attached came off the mountainside and they floated in the lake. And of course, the ones with root balls, the root ball is heavy and the roots are heavy and they drug the tree down and then the tree stuck to the bottom. We see a fossilized situation like that, Specimen Ridge in Yellowstone, where you have various different stumps that are all sitting in this hillside, piled up all on top of each other. And during a giant volcanic eruption, they all were ripped off wherever they were and buried, all stacked up on top of each other. Where normally stumps are going to, of course, be rotted away and destroyed, etc. So this is a way of preserving stumps. It's fascinating. So that's most likely how these stumps came to be. Again, I'd like to actually examine it more, but from some of the photos I've seen, it kind of indicates this kind of layered type environment, which would lead me to believe this is probably a debris flow stump. So here's a closer up picture. You can see it's wood. It's like you could carve it, they say. You can light it on fire. It doesn't smell like wood. That's the one thing over time that's lost its smell. But otherwise, in every other way, it seems to be wood. And the northern Arctic, with the very cold environment, has seemed to be a preserving agent, kept it from rotting away. Bacterial activity. Bacteria just doesn't tend to like to thrive in really, really cold environments. So, I mean, that's the reason why we have a freezer and a refrigerator. You get it cold, and the bacteria doesn't spoil our food. So, here is this chunk of tree material from Wikipedia. So very fascinating piece of wood. Here's some articles here we could jump to, but I'm going to skip past them. But if you look up on Google, you can find all sorts of very interesting articles and photographs of this phenomena. So I want to pause here a little bit on the kinds of trees that we have here in this environment, because this is very, very unexpected. So birch, horse chestnut, pine, spruce, cedar, ginkgo, dawn redwood, Chinese swamp cypress, but also modern tropical forest trees, magnolias and ferns. You got magnolias growing here in Tennessee where I live in. Large monocots that resemble palm trees. Ooh, so a palm tree-like creature, like plant. That's fascinating in the high Arctic. Palm trees in the high Arctic. They're related to the ginger family. Fossil evidence suggests the Florida neighborhood might have been a bit like modern-day temperate rainforests of British Columbia, as well as the swampy, diverse ecosystems of Georgia and northern Florida. So you see kind of a collection of different flora that doesn't really match a specific ecosystem today, but kind of a rainforesty environment where elements match like Florida and Georgia and some like British Columbia. And there's the fauna suggests actually more of a tropical-ish environment than the flora suggests. Because as we drop to that, we've got tapirs. And these are tropical type creatures. Alligators, crocodiles, those would fit the North Florida type environment. In fact, in the Okefenokee Swamp, I've stood about 18 inches from the head of a big guy like that. That was quite interesting. He just looked at me and we looked at him and we didn't bother each other. So that's pretty fun. So here's some other creatures. A lot of these creatures from the Eocene are no longer with us today. They're extinct. But we have this otter-type creature. We have some primates like lemurs. I'm not sure, like a hippopotamus sea creature. I won't even try to pronounce these because I don't have much expertise in paleontology. But it kind of gives you an idea of sort of an environment that would exist. Definitely nothing even remotely like it is today. The closest would be like a wolverine, which typically lives in northern environments today, northern Canada and so forth. But even this area is far, far too north for a wolverine. So I don't even know how to characterize this creature. This creature kind of reminds me a little bit of the warthog in some respects, although I'm sure it was quite different. And again, we're seeing the artist's rendition, which I'm not sure how much we can extrapolate from that. But it would kind of gives you a tropical type feeling. But here's our problem. We're right here. I mean, it would be closer to get to the North Pole than find the nearest Taco Bell. This is strange. You don't find tropical creatures living up here next to the North Pole, like, the alligators and the polar bears. No, they don't live anywhere near each other. This is very strange. What's particularly strange is that there are Eocene deposits, like the Green River Formation, which is down here somewhere, that match climatically what we're seeing up here. So this gives us the concept that there is an equitable climate in the Eocene from the North Pole to the equator. That doesn't make any sense because the sunlight doesn't reach up here for months on end. And what makes it even more complex is that you've got Asia here. This is an Eocene layout. It looks very similar to today, but you might notice some differences. There's not much of a gap here between Greenland and Scandinavia. Europe, the Atlantic Ocean is just not as wide at that point. And you don't have a lot of room for major flows of water from the tropical regions to come up through the Arctic Ocean. You kind of have this little lake up here, if you will, a big lake. And I've heard someone's suggestion that, well, we'll solve the equitable climate problem by saying that warm, moist air was blown up over the Arctic. Like, wait a minute here. I know what happens to warm, moist air. You take it and you bring it over an area with no sunlight. it gets cold. When warm, moist air gets cold, it precipitates. And if it gets below freezing, which it certainly would, then this is just going to turn into one giant ice cap. This is ice age. Warm, moist air in a cold environment turns into an ice age. That's how you make an ice age. People think ice age is just cold. No, no. You got to have the moisture to add the ice. That would ticket for an ice age. So there is no answer for the equitable climate problem if you consider this using standard geology. Now, as some of you guys know, I don't believe in standard geology. In fact, I believe the evidence does not point at standard geology, and we have to come at it from a different worldview, completely different perspective. So back in the 1990s, there was a group of creation scientists who were grappling with a similar set of problems, not this one in particular, but they were looking at continental drift. Continental drift is a very powerful theory. It explains a lot of what we see. We've got mountain ranges here in Europe that match the Appalachians. We have fossilized remains in places that, same fossils over here in Europe match the fossils over on the North American continent. That happens between with Africa and South America and so forth. There's clearly these continents work together. I mean, you just look at a map, looked at it as a child, and I'm like, South America fits into Africa. North America slides up next to Europe. I mean, it all fits together. So there's really no question that the continents were together and they split apart. The question is, how did that mechanism happen? Was it, like continental drift theory states, a slow process that went where the continent thing is that your fingernails, as they grow, they will, that's about the rate at which the continents are moving. And that is the rate the continents are moving today, thereabouts. But was that the same way all the time? Well, it turns out that if the continents move fast or the continents move slowly, the same predictions of continental drift prove out to be true. However, if you take the model where the continents were at a position of essential stasis like they are today, and then you introduce a few months of incredible movement and breakup, where the continents move to their current positions and then return to stasis. If you look at it that way, that answers actually a bunch more questions that the typical plate tectonics doesn't answer. So they call that model catastrophic plate tectonics. So taking the catastrophic plate tectonic model and applying it to the equitable climate problem is an interesting way to go, does catastrophic plate tectonics solve the equitable climate problem? And so let's dig into that a little deeper. What does that mean? How does that actually work? So here's a little bit here about the catastrophic plate tectonics theory. And basically what I'm getting at is the Eocene is no longer an epoch in which animals lived. It's an epoch in which plants and animals were buried. So they lived in a previous epoch. Then as the continents moved to their current locations, they were buried in a sequence. And the Eocene is part of that burial sequence. So let's dig into what does that look like. So here's my hypothesis. The islands of northern Canada were located in tropical subtropical region. Then they were buried later near their current location. So obviously the first thing we think of is, hey, Pangaea. It's the supercontinent. The supercontinent broke up, moved into its current position. Hey, let's look at Pangaea and see. So I found a little model here on the Wikipedia of Pangaea, and let's look. So we've got here Hudson's Bay, the normal outline of North America as we're used to. Florida's down here, Mexico's over here, etc. Right? Great Lakes, you kind of see them right there. And let's go up here to the very northern part of Canada. You've got Axel, Heiberg, Elsmere Island, Greenland. Yeah, but that's still quite a ways up here in the north. You would not expect this to be a hot, swampy environment. Equitable climate problem still exists. This did not solve it. However, Pangaea is not the initial starting state of catastrophic plate tectonics. Pangaea is an intermediate state where life was being buried on the continents as they were moving. In fact, the name Pangaea is all life. It describes the fact that life is buried on the continents during this configuration. So while the continents were in this configuration, life was being buried and later fossilized, thus giving it the name Pangaea. So let's go back to a formation of the continent that predates Pangaea, because Pangaea is a burial epoch, just like the Eocene is. It's a transitional state from the catastrophic plate tectonics theory perspective, which I believe is probably the best model we've got today. So let's go back to Rodinia. Now, Rodinia, I do understand that there's some debate on how the layout of the continents is. This is just one picture I found online. How accurate it is, I don't know, but it is fascinating that it is significantly different in a significantly fascinating way. North America is now on its side. It's called Laurentia at this point. You can see Hudson's Bay here. This would be where Alaska would become. You've got probably Maine over here, northern Canada reaching up above Maine. Greenland is over here. You've got Elsmere Island and Axel Heiberg, and right about here. Note, you've got the equator running through here. So this is sitting right here in a kind of a tropical, subtropical zone. It would very much fit the kind of environment that we would expect for these kind of creatures. Furthermore, if we go west and find the Green River Formation somewhere in here, the southwestern Wyoming, it fits the same latitude, same kind of environment, but it is an inland environment, so it would the more the high grassland type remains found there would fit that kind of environment that we find here in Axel Heiberg. So if this is the correct configuration of the continents before they broke up, then this is exactly the kind of life that you would expect to find on that kind of latitude. And it actually fits. There is no equitable climate problem because instead of going from north to south, we're dealing from an east to west perspective. So I think it's pretty exciting. It would be interesting to look at more sites and compare the flora and fauna to the layout here of Rodinia and see if it maps up consistently. And my bet is that it will map up consistently, just like the Axel Heiberg and Elsmere Island remains map up as well. And if it doesn't, it's likely because the plotting of Rodinia is wrong. So that would be an interesting. Now, of course, we're taking a theory and using it to apply to understanding our data. That's a risky thing to do. But nonetheless, I do think that this is an interesting area of potential research that could be used to explain a lot of sites that today are confusing. There's similar remains being found in Antarctica, and I'm sorry, here it's hidden behind my picture. I'll disable that here briefly. Wrong one. There we are. No, that's not Antarctica. Where is Antarctica on this? Anyway, we that is also explained by the plant remains being in a Rodinian-like configuration versus where they are currently. So I think there's a lot of room for growth and explanation in looking at fossil sites and then mapping them back to a Rodinian configuration, which is very exciting. And it's really cool to see how some of these theories that were created back in the 90s can be used to explain more recent discoveries. So to go back to our, here, I'm going to go back to my slide thing here. So that's pointing again at Elsmere Island area, Axel Heiberg. And if we go back to our original title of the talk, I called it an Arctic story. Well, it's not. It's a tropical story. Thanks again for joining. I hope that you enjoyed this.